So first we need to define what a thermal time constant is. The thermal time constant is the time it takes for the energy, or for the system to change 63.2% of the delta T that we are expecting, and the expected value would be at T infinity, or the temperature of the ice water or boiling water. This being said, that if we take the thermocouple and we know the thermal time constant of the transferring of heat from the thermocouple to our system, we should see a time period in which the temperature difference has dropped to 36.8% of the initial difference between the temperature of the system and our thermocouple. So this is a chart taken from Mitsubishi Materials, and it's explaining the difference between the thermal time constants and after we pass different thermal time constants, where we would expect for our new temperature to lie. And so this is the experiment results, the raw data, and I marked up the boundary conditions for where we put the thermocouple into the water and where we took it out of the water, and then where we took the thermocouple out of where it started drying off and reaching room temperature, and then where we say that it reached room temperature based off of the data that we received. So the experiment results, we expect that because the time taken to cool the thermocouple based on the boundary conditions that I marked is 20 seconds, that our time constant should be expected to be about 4 seconds, which would be 20 divided by 5. From our differences in temperature, we see that the first time constant should bring a difference between the initial temperature and the final temperature to 36.8% of the initial difference. So the initial difference was about 20.9 degrees, and then the new difference would be about 7.69 degrees Celsius. So then I ended up graphing the predicted results to the actual results for our predicted time constant. So the predicted results show that after the first time constant, we would reach a 36.6% difference, and then a 13.5% difference would be which was 36.6% of the 36.6%, and it goes on until we reach 0.67% of our difference, and we have a logarithmic change. However, whenever we go and compare it to the similar times from the actual data points, we get a difference of, after the first time constant, 11.2% difference, going down to 7.5, then 4.83, then 2.8. And it's significantly closer after the first time constant than what we expected for it to be, which was a little bit abnormal within these results. So then also there's a note that this is before we use the logarithmic mean to calculate the time constant. This was the estimated time constant. So the logarithmic mean is seen in equation number 4 from the lab manual. It's that ln of t minus t infinity over t naught minus t infinity. And so within this experiment, we were asked to calculate the logarithmic mean, which is used to, within change in time, to calculate what the time constant should be based off of our starting temperature and the final temperature that we expect, and the measured temperature. So this is whenever I plotted the logarithmic mean within respect to time, and I also did the same thing where I plotted the time on the x-axis and the logarithmic mean on the y-axis. However, whenever I interpreted the results, I took the time and I did the time difference over the logarithmic mean difference. So I got a time constant with the units of seconds. And so here I did the same thing as I did on the previous chart, where I listed the boundary conditions. And what's interesting here is that we can see that we don't exactly get a linear curve or a linear fit from our entering the thermocouple into the glass of ice water and taking out the thermocouple from the glass of ice water. And it's more linear from the thermocouple and air to the thermocouple in equilibrium with the air. So after we go through and do the math, I showed how I did it over there, but for the cooling of the thermocouple in the ice water, we get that equation, which is using our boundary conditions from our change in time over the boundary conditions from our change in the logarithmic mean. and we get a the thermal time constant of 3.34 seconds based off of that, which is different than our predicted, which was 4 seconds. And then similarly from whenever we, I did the same thing for the boundary conditions from the, because we're expecting a linear change, I took the boundary conditions and I did the average slope rather than doing the curve fit, which describes basically the average slope. And I did the same thing for the thermal time constant between it warming up from the air, and I got 135 seconds as our thermal time constant. And so we have to then go ahead and analyze why is our thermal time constant different from whenever we have it in the water versus whenever we have it in the air. And from this we can look at equation number 3, where we look at the thermal time constant is equal to the density of the thermocouple times the volume of the thermocouple times the specific heat of the thermocouple over the convective heat transfer. And we can also look at this chart, which I found from this nuclearpower.net, which explains that whenever looking at free convection, the convective heat transfer of gases is significantly less than the convective heat transfer from liquids. I didn't analyze the boiling one, so I didn't get to see that result, but I did look at that, and that explains those. So calculated versus measured, we can see that based on our result, this was essentially what I explained earlier, where there was a difference from 4 seconds from our predicted to 3.34 seconds from our calculated thermal time constant. And then going here, we can see from the results found in the calculation, due to the smaller thermal time constant, we started our experiment with a closer match than expected. So from the calculated thermal time constant, our initial difference from the first iteration will be 15.64%, and then it'll go to 8.56, and so on and so forth until we get to 2.57 after 5 iterations, which doesn't necessarily make sense to what it should be predicted. And I feel like there are slight errors within the experiment which may cause this. So possible sources of error is that, so first of all, within this experiment, one source of error is that the static water, as the water surrounding the thermocouple heats up, it then requires for that water to, for the heat in that water to dissipate before allowing for the thermocouple to continue cooling off. Also, another potential source of error is that we possibly couldn't have cooled the cup of ice water enough. And then the final source of error that I found is that if the thermocouple is in held in static position, we're not going to get necessarily accurate readings. Preventing errors, so we could have some sorts of flow in the water to induce forced convection to prevent the static water. However, this would change the experiment because we'd be looking at forced convection versus free convection. And then we could wait an amount of time to make sure that the thermocouple is for the glass of water to reach a stable temperature. We could also make sure that we attach the thermocouple to a stand, preventing human error from the thermocouple moving and possibly hitting the walls. And then I feel like also if we needed to wait longer before taking the thermocouple out of the water to make sure that we got a full set of data rather than just a partial set of data. And then there are my sources. Questions? Yes, sir.